Hello, this is a recording on for the triple integrals lecture. Okay, so today we will start with triple integrals. We will do triple integrals in three coordinate system. The Cartesian, the cylindrical, and also the spherical coordinate system. I will just introduce later each of these coordinate system. I will start with the Cartesian coordinate system. So this is the usual x, y, z. So, but first, let's recall that last time we have two coordinate system for double integrals. The first one is in the Cartesian coordinates in the xy. And then the second one is for the Cartesian coordinates, we get dA is equal to dx dy or dy dx. And here we get dA is r dr d theta. So today we will do cylindrical and Cartesian, but in the case of polar coordinates. So first, let's start with our topic, triple integrals. So what's a triple integral? So a triple integral is just an integral on two variables, in a function of three variables, x, y, z. So here we get a function of three variables. This is in the set. We will set first in Cartesian. So here we will do it. In Cartesian coordinate first, and then the same will be the setup for cylindrical later. Here we get a function of three variables over S here. This is the solid S in R3. Okay. So that's it. So let us define the double integral. So what happens really is you get a solid. This is in, say, R3. So let me draw the coordinate system. This is X, Y, and Z, and we have a solid. And here we have a volume, this one, small box inside. And then this has volume delta IV or delta V sub I. So this is just equal to, the volume is something like delta I X, delta I Y, and delta I Z. So this is just the length, width, and height. And to each volume element, you get a function. You get a point xi, yi, zi inside this box, small box here. This box, differential box, and then what we want is to get the function multiplied by the volume. So the product is you get xi, yi, zi, and then multiply that with delta vi. So this is the volume of, no, it's not, it's just the, at each volume, we associate this value. And what we will do is we form the Riemann sum. The sum is you made this into finite number of boxes. So here, so I from 1 to n of f's xi, yi, zi, and then delta iv. So this is your approximately equal to the, this is your Riemann sum. And then the triple integral, so here the triple integral over the region S of the function x, y, z, dv is just the limit of this Riemann sum from 1 of xi, yi, zi, delta iv as n goes to infinity. So this is similar with, you notice that in double integral, this is similar build up. Recall that we have the following. So we have a region and we take a box here, and then this is the AI or something like that. And then this is just delta ix or delta iy. And then the double integral over this region R of our function of two variables x and y is just the limit of the sum I from 1 to n, 1 to n of f of xi, yi, delta I, a. So this is your double integral. So you can look at the similarity of the build up here on double and triple integral. Here is x and y axis. So that's it for our conceptual uh, understanding of triple integral. And then we just recall the double integral. Here is y-axis. Oh, it's separate. This y-axis is this axis, and this x-axis is this axis. Of course, it's the origin. Okay. Now let me do some remark. So the first remark is your dv is equal to dz dy dx dy or any permutation of this. So there are six arrangements or permutations. So example of that is d z dy dx. So the interchange here y and x, and of course you can go with dy first and dx dz. So and then others. And the second remark is the following. Last time we have the area of the region is just 1 dA, is the area. Now the volume of solid S is just equal to the triple integral over our S dV, and then we just have 1 dV. So this is your volume, this is your area. So triple integral here is like the if your function is just 1 dV over S, this will give you the volume. Okay, and of course, z, x, y is it directs the order of the iterated integral. Of course, with respect to z, then in the inner one, you get with respect to z first. Okay. All right, let's do an example of triple integral. So here we will first do a quick example wherein we solve a triple integral here from 0 to 3, -1 to 2, and then 0 to 1, x, y, z squared, and then dx, dy, dz. You have direction is to evaluate this integral. Evaluate this integral. So solution. So as I have mentioned to you before, I prefer that you decompose it into like individual integrals, so it's easy for me to check your answers. So the first integral will be from 0 to 1. This is the inner one. So this is the inner one. The inner one integral, or whatever the naming you want. So x, y, z squared with respect to x. So here we treat y, z squared as something fixed. So they are treated as constants. So y, z squared, and then you get x squared over 2, and then 0, 1. So we get here 1/2 y, z squared. Okay. Now for the second inner, we have -1 to 2 of the output here. 1/2 yz squared with respect to, this is the inner 2, with respect to y. Okay, all right. With respect to y, you get 1/2 here, z squared, and then y squared over 2, and then integrate from -1 to 2. So we will simplify further. So we have 1/4 y squared, z squared, and then y runs from -1 to 2. All right. So this is just 1/4 z squared, and then 2 squared minus -1 squared. So we get 4 minus 1 is 3/4 z squared. So this is the output for the second integral. And now we go to the outer integral. So this is just 0 to 3 of 3/4 z raised to 2 dz. So this is just 3/4 z raised to 3 over 3, and then 0 to 3. Here cancels, so we get 1/4 z raised to 3, then 0 and 3. Now we got 1/4. This is 3 raised to 3 minus 0. So we get here 3 raised to 3 is 27 over 4. So this is your final answer. So that you conclude that the triple integral was the original integral 0, -1, 0, and the upper one is 3 to 1 of x, y, z squared, dx, dy, dz is just 27 over 4. Actually, it's okay that if you end here, but if you conclude properly, it's like a bonus for me. I mean, I think that's good for me when I'm marking your work. Okay, this is the case where in our region, or this is our solid is just a box. So this is just something like this. That means all your boundaries are just constants. So in this case, it's easy to evaluate by changing the iterated integral. But there are cases wherein the bounds are not anymore like constants. So let me consider a second example, and then we will do the this ones. This is a module example. Notice that in my previous handouts, I have very few examples during the last semester. This is due to the fact that we have a lot of suspensions during that time, and then the discussion is a little bit compressed. So now I have like more time now because of very little suspension, like a minimal suspension. Okay, so let's continue with the next example. So our function here, x, y, z, is just xz. And then the solid is given by the surface. The solid is under the surface x plus y plus z squared is equal to 4 in the first octant. So when I say first octant, so this is your this is your x, y, z. The first octant is this part here, because of course this is in the quadrant 1. This is in the quadrant 1 in the xy plane, and then positive of values of z. So, okay, let me rephrase positive. I will include a 0. Okay, let me erase this one. It is in the first quadrant, and your z here is greater than or equal to 0. So that's what's meant by the first octant. Of course, there are here we have, this is octant because there are 8 of them. So this is the second quadrant. This is the second octant. and then Z is also positive, and then the third octant, fourth octant, and so on. But most of the time, we will just deal with the first octant because of the symmetry and the nice thing going on here. So here, if we are going to draw this region, let me draw that here. So although I can copy paste in the handout, I prefer to draw it because, yeah, for the reason that I told you before. Okay. So this is your surface Z plus Z squared plus X plus Y is equal to 4. And we want to set up the triple integral over the solid S. Here, the solid S is the entire solid here, bounded by the XY plane and these coordinate planes. So the first we just consider the first octant, and then it's bounded above by this surface Z squared plus Y plus X is equal to 4. And then the function is XZ dV. So we want to set up. So first, we are going to choose our dV. So let's do that when your dV is dz, dy, dx. Okay. So here, how do we set up? When z is equal to 0, this will become x plus y is equal to 4. So in the xy plane, this is your x, this is your y. X plus y is equal to 4 is this line. Okay. Is the line x plus y is equal to 4. When x is equal to 0, you get y is equal to 4. When y is equal to 0, you get x is equal to 4. So this is the somehow the shadow. This is the shadow in the xy plane. Okay. Now, so the triple integral, this triple integral here over S of xz dv will be equal to the iterated integral and then xz, and then we have our chosen dv, dz, dy, dx. Of course, for x, we will start with the origin 0 up to 4. So that comes from here, x, 0 up to 4. Then for a fixed value of x, we get our y is from 0 to, what's y here? Y here is, this means your y is 4 minus x. So this is from 0 here. And then the end part is, the upper limit of here is y as function of x is 0 and then 4 minus x. Now for the z, it is bounded below by the xy plane, so it's just 0, z is equal to 0, and bounded above by this. But you want to express z in terms of x and y, so it's just 4 minus x minus y. So this is the setup of the triple integral over S of x z dv when we are going to choose dz, dy, dx as our order of integration. Now, for the second one, I think I will copy this one so I can use it again here. and smaller. Okay. So in now we want dv be dy dx dz. All right. So now here we get to um this is our x, this is our mm, this is our x, this is our y, this is our z. Now we look at the, okay, I think I made a mistake here. So it's supposed to be y here, and this is our x. And then I will erase this one. dy, dx, and then dz. The second one is, okay, let me correct this one. Second one is dy dx dz. Okay. We know that this is 4, this is 4. What about this? When x and y is equal to, here, the point here is x, when x equal to 0, y equal to 0, z squared is equal to 4. That means z is equal to 2. So this one is 2. Okay? Okay. Now, we are going to look at here. So this is your region. This is your z. This is your 2. This is, the equation here is, we don't have y, so z squared is equal to, is plus x is equal to 4. Because in this case, your y is 0. This is the zx or xz plane. xz plane. So in the xz plane, y is 0. So this is your somehow shadow. So the triple integral over s of xz dv is equal to this iterated integral xz and then dy dx dz. Here, if you look at our z will run from 0 and end with 2. Okay. And in our x as function of z, here x will be, let me draw this. X will be here. This is upper x, lower x. So this one in terms of z is 4 minus x 4 minus z squared, x in terms of z, and 0. And then here, it's just from the xz plane, so that's y is equal to 0. And then we end with y plus x plus z squared is equal to 4. Then solve for y in terms of x and z. We get 4 minus x minus z squared. So this is now your iterated integral when when your order of integration is dy dx dz. Okay. So here you are looking at the shadow in, or like the region in the xz plane, and then here the upper y will be in terms of this, and the lower y will be just the xz plane. That's it for our this example. Before going further, let me do our example, similar example in the previous double integral. So here we get the solid is bounded by your surface. Z is equal to 4 minus x squared minus y squared. This is bounded by this above, and below by z equal to x squared plus y squared. And then we know last time that this is your z is equal to 4 minus x squared minus y squared. So this is your z upper, zu, or z upper. And then here z is equal to x squared plus y squared. This is your z lower. And what we did last time is to set this up, but here it's 6 in terms of double integral. Now we will set this up in terms of triple integral. So we need to, this is y, this is x, this is z. So what we want here is to set up the triple integral that gives the volume of your solid S. So the triple integral is just S dv. All right. So here we will choose the convenient, with this setup, the convenient dv is dz, dx, or dy dx, or dx dy. It's okay. Dy dx. All right. Now, here, this is the chosen order. Now, the second item is to look at the shadow. The shadow here in the xy plane. So what's the equation of the shadow? So here, as before, we get, this is the region where z upper is greater than or equal to z lower. So this is 4 minus x squared minus y squared is greater than or equal to x squared plus y squared. Now we get 2 is greater than, this is just, let me do it step by step. So here we have 4, here we get 2x squared plus 2y squared. And if we divide both sides with 2, you get 2x squared plus y squared. And then this is the region here bounded by x squared plus y squared is equal to 2. So circle of radius square root of 2. So here, this is negative square root of 2, positive square root of 2, square root of 2, negative square root of 2, and that's y-axis and x-axis. All right, now we have the shadow. Using, this is how to get your region R, which is your shadow in the xy plane. So these are two paraboloids. So the solid is intersection of two paraboloids. Now, okay, we have everything we need. So the integral here, dz, is 1, dy, and then dx. So the inner integral will have bounds here upper bound is just 4 minus x squared minus y squared, and the lower bound is x squared plus y squared. So this is the z lower, and then this is the z upper. Okay, so let me encircle this. Is not part of the solution. It's just a comment. And then for y, we look at this. So for each x, let me draw this in different color. Our y is, in terms of x, it's bounded above by positive square root of 2 minus x squared, and then negative square root of 2 minus x squared. And then our x will run from negative square root of 2 to positive square root of 2. So this is the volume of our solid S. So this is the volume of S. Okay, volume of S is given by this integral. All right. This is just the setup. You notice that it's hard to compute. That's why we will use other coordinate system. But before moving forward to other coordinate system, let me discuss one example on the module. This is example number 3 in page 25. Let me discuss this quickly. So our solid S is bounded by z is equal to 4 minus y squared, and the plane x minus y is equal to 0. So in the first octant, again, it's just the first octant, so we just draw this is your x, this is your y, and this is your z. We just get the first octant. So the surface x plus y, x equal, the surface is, this is the surface. So it extends upward, but the solid is bounded above by this. Now I think I have made a mistake in the surface. Let me correct that. The surface is x plus y is it's not x plus y, x minus y. So x minus y is not that. So we erase. X minus y is like this. Okay, it's not straight. So let me, assuming this is straight, and then wrong. Okay. So this is the equation is, this is the equation of the cylinder. This and this one is the equation of plane. So the equation of the cylinder is it's like this at the back, and then it goes like this here also. Let me draw this separately. And this is like the back part, and this is the front part here. All right. So this is the equation. X is equal to what? To x minus y equal to 0. X minus y equal to 0. And then the surface above is given by z is equal to 4 minus y squared. So now, what we want is get the setup, the triple integral over this solid S 1 dv. All right. The first order of integration that we want is, what's the first? Let me check my notes here. Okay. dv is equal to dx, dz, dy. So in that case, we'll have this triple integral. Let me use black. This triple integral over the solid dv is just this iterated integral, and then dx, dz, dy. Okay. Now we look at the shadow, this part here. So that part we will draw that here. So this is the y, this is the z, and this is the yz plane. The yz plane, the equation is x is equal to 0. Of course, when x is equal to 0, we just have z is equal to 4 minus y squared. Okay. Now here, when z is equal to 0, what is y? When z is equal to 0, y is equal to square root of 4. We just take the positive because in the first one. So this is 2 here. And then we see, so here it's 2. And then above, when y is equal to 0, we get z is equal to 4. So in this case here is 4 here, it's 2 here. And then since x minus y is equal to 0, we get this part here 2 also. Now we are ready to set up this integral. So our y will run from 0 and end with what? Where's y? So it will end with 2. So this is from 0 to 2. And then our z will run from, with a fixed y, z is equal to 0 and end with z is equal to 4 minus y squared. So let's write that out. So z is equal to 0 and 4 minus y squared. And lastly, our x will run from, x here is x minus y is equal to 0. It will be starting from this here, this plane, x equal to 0, and then end with x is equal to y. Okay, so this is now the triple integral that will give you the volume of this drawn solid using this order of integration here. All right, let's do another order of integration. So let's say, of course, you have to check this will be, you have to check that this will be equal to 4 when you put it in your calculator. Okay. Let's do the other order. The other order is dv. Let me use black. dv is equal to dz, dy, dx. In that case, we have our region R in the xy plane is like this. So this is 2. This is your y, this is your x, and this here is 2, and the equation of this is x minus y is equal to 0. That means that x is equal to y. So now the triple integral over s dv will be that this triple integral dz, dy, dx. Our x will run from 0 up to 2. And then for a fixed x here, our y will run from x y as function of x. So here we get x. All right, let me x as lower bound, and then the upper bound is constant 2. And then of course, for z, we have it's bounded above by the 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 surface, which is the cylinder, given by 4 minus y squared, and bounded below by the uh, xy plane, given by z equal to 0. So this is your triple integral. So you have to verify this gives 4 if you evaluate, and then you compare it here, it's also 4. And lastly, if you have C, you're looking at this triple integral of S, then dv. Okay, let me write this again. See, when you use dv is equal to dx, dy, dx, dz, then what you will get is here in the yz, this is your x, your z, and here you just also have our equation, but here since x is equal to y, you get this is also z squared is equal to the original one. So z is equal to 4 minus x squared. Okay, so here the triple integral that gives you the volume is given by this triple integral. So dy, dx, dz. For our z, it will start with 0, as we have noted earlier. So 0 to 4. And then for our x, so our x will start with 0 also. And then here you get x as function of z. So x is equal to 4 minus z square root. So 4 minus z. And if you get our y in terms of our mhm, our x and z, you have at the upper equation, you get also square root of 4 minus z, and bounded below by y is equal to x. So also, this will give you 4 if you evaluate this. So if it's not very clear, you can like verify this, but this is your, I mean, repeat the process of getting the this one. So here, if I will draw this here, you get, this is the shadow here, but it's something like like this. This is your y upper, and then the equation here is y lower, y upper. So y upper is given by this, and y lower is just x. And then for the shadow in the xy plane, it's just this one, this shadow. So this is 4, and this part here. You have to verify that. Now, I think that's all for the examples that I'll discuss. I will leave the example on the sphere as exercise for you. Now, I would like to remark usually we use dz dy dx or dz dx dy because eventually we can translate anything and then put x and y as our variables. It's easier and then it's usually done this order. Okay, now let's go back to our triple integral earlier. So it's just square root of 2 negative square root of 2 positive square root of 2 and then square root of 2 minus x squared negative square root of 2 minus x squared, and you get here 4 minus x squared minus y squared, and then below is x squared here plus y squared d z d y dx. So this is your original, I mean the example earlier. So here if we solve the inner integral, you have 4 minus x squared minus y squared, x squared plus y squared, and then dz. You get z and then x squared plus y squared, and then 4 minus x squared minus y squared. And what you get is 4 minus 2x squared minus 2y squared. Now for the inner second integral is just negative square root of 2 minus x squared, square root of 2 minus x squared here. And then you put here 2 minus 2x squared minus, 4 minus 2y squared. Okay, let me pause a little. All right. And then you are going to do is, what you're going to do is plug in here our negative square root of 2 minus x squared and 2 minus y squared. And again, this is hard as I have noted in the outer integral. I will not finish. I'll skip this part. As I noted earlier, it's hard. So the solution is, earlier we switched to, is to switch to other coordinate system. And then that coordinate system is using the first coordinate system that we will introduce is the cylindrical coordinate system. Cylindrical coordinates. Cylindrical coordinates is easy because we have the conversion x, y, z. And then this is the point in R3. So we have y here, x here, and z here. And then this is your Cartesian. And then for cylindrical, you get, suppose this is this one. So you have, it looks like a cylinder because here you have the level z, and then this level, at level c you get the angle and then the radius, and then project it upward at level z. So you have in this Cartesian, and then in the cylindrical, it's r, theta, and z. This r and theta is from polar. And of course, we know the following: x squared plus y squared is equal to r squared. And then tangent of theta is y over x. Okay. And what else? There are other identities that we have encountered before. So what's the other? the x and y in terms of r and the angle. Okay. So let me review. Okay, for the cylindrical, we get the following. X is r cosine theta, y is r sine theta, and what else? Okay. And of course, here, your dA here is, I mean, dV here is dx, wait, dz, dy, dx, or permutation of this. Here, for cylindrical coordinates, of course, the z here is the same as the z in the cylindrical coordinates. And the volume element, your dv in polar coordinate, in cylindrical coordinate is like, this is your dv is just d dA and then times dz. And from polar, it's just r dr, r d delta theta, and of course dv will be r, and then here we have dz, here we have r dr d theta dz. So this is your dv in our polar coordinates. So this is your volume element in polar coordinates. And now it is given by this triple, r, theta, z. And r theta came from um, the polar coordinate system that we have. Okay, let me now write our original integral in uh, in XYZ coordinate to polar coordinate. So in polar coordinate, we will write this as the same one, and then dv will be dr. But or permutation of this, but the commonly used is this, r dz, dr, d theta. So let me put that here, dz, dr, d theta. Our theta will run from 0 to 2 pi. And then our r will run from 0 to square root of 2. And our z will run from this to this. X squared is just r squared, and then this is 4 minus r squared. So this is your triple integral in polar coordinates. All right. So here, so already we have the comparison. Here is our dv for Cartesian, our dv for cylindrical is the most common use is r, dz, dr, d theta, and then here z is in terms of r and theta, and then r is just the what I told you earlier, like the scaling factor. Now let us survey some equations in for example, if we have this is our y, x, z. If you get theta equal to alpha, this is just theta equal to alpha determines a plane. And then the plane is given by this plane. Okay. Yeah. This is the plane parallel to the z axis. All right. I think I'll end here with polar coordinates. Of course, if you're going to look at your module, there are more examples there. So, uh, okay. Of course, example. The example here in the module is this is a function of first it's xyz. This is xyz, and then um, it's enclosed by our sphere. It's considered as the function xyz on S enclosed by the upper hemisphere of x squared plus y squared plus z squared is equal to 1. Upper hemisphere means you have, this is just half the sphere. This is your solid S, upper hemisphere. So now what we want is to set up f dv in cylindrical. So first is to compute or to convert xyz into uh, r theta in terms of r and theta. So this is x is just r sine, x is just r cosine theta, r sine theta, and then z is just z. So we get z times r squared cosine theta sine theta. So this is your new f of z. And now the upper this integral s f dv is just the following. The iterated integral given as follows: r squared z cosine theta sine theta times r dz dr d theta. Of course, your theta will run from 0 to 2 pi. Okay. And your r is um, it's bounded by 0 to 1. And then here our z is from 0 to square root of 1 minus r squared. Okay, that's it. That's it for our example on notice that in the module there's a typo error on this part here. It's supposed to be 0 to 1. This is your triple integral of the function. So you make sure that the function here is in terms of theta, r, and z. So here we have r, theta, z, so walang x and y. And then we will use this, usually we will use r, d, z, d, r, d, theta for our dv. I think I'll end here. And then next time, we will do spherical coordinates and more examples. I think it's better drawn or work in the class. More examples on cylindrical, and then examples on setting up in 3 coordinates. Like we have a single solid and then set up in uh, set up here in three coordinates system. So we have a solid S, we will just set up in Cartesian, we have set up in cylindrical, and we will also set up in spherical. I think that's all for today. I'll end the recording.